Hey everybody, it's Dr. J, and today we're talking about magnetism and molecular orbital theory. Let's talk chemistry. This is really dealing with molecular orbital theory. Please check the previous videos to learn more about molecular orbital theory. Essentially, if you're diamagnetic, you're going to have paired electrons, right? One going up, one going down. So most compounds are actually going to be diamagnetic because we understand that, right? They like to be paired, right? It's more favored to be a paired electron. But we also have paramagnetic, all right? So this is when you're going to be attracted by your magnetic field. So we're really going to see this when we have unpaired electrons, right? And, like I mentioned before, these are very rare. It's not that many compounds that are actually paramagnetic. Now, let's look over here to some trends. As bond order increases, bond energy will increase. Therefore, if your bond energy increases, your bond length will decrease, right? So we learned about that with our bond trends, right? And if you want to learn more about that, check out the previous video about bond trends. And if we look over here to this chart, it kind of explains these things over here, right? That's the reason why molecular orbital theory is crazy, right? This gives you so much details just by doing this theory. If we look at B2, this is our molecular orbital theory. So we got our electrons in each of the shells. In this case, we got sigma 2s, sigma star 2s, pi 2p, sigma 2p, pi 2p star, and then sigma 2p star. And then once again, this order is following boron, carbon, and nitrogen. And then we have a different order for oxygen and fluorine with our, in this case, our sigma 2p changing with our pi 2p. And once again, look at our previous video to learn more about those molecular orbital theories. But once we do our molecular orbital theory, right, we're going to find a bond order. In this case, 1 for boron, 2 for carbon, 3 for nitrogen, 2 for oxygen, and 1 for fluorine, right? And once again, bond order we find by doing the bonding electrons minus our anti-bonding electrons divided by 2. But what we see here is that we get determined, in this case, a bond energy as well as a bond length. So N2 is going to have a triple bond. We see that with the bond order being 3. Triple bonds have an extremely high energy. In this case, N2 has 942. And we can see that the bond length is very small because of this high bond energy. Okay, so pay attention to that trend. Bond order does not completely predict bond energy. And that's because of molecular orbital theory, right? We could kind of determine some of these things now. For instance, B2 actually will have be greater than F2, even though both of them have a bond energy of 1. Okay, F2 also will have has much electron repulsion, and because of this, it has a weakening bond energy in this case. All right. And if we think about N2, in this case, the bond order will be 3. The triple bond is very strong, and that explains why N2 is unreactive.